Good afternoon, and thank you for attending my presentation today. I am really excited to be part of the AI in Retail Virtual Summit this year, and I hope to share some useful insights with you. The title of my talk is Data Science Applications in Retail Pricing and Promotions. But let me first start by introducing myself briefly. My name is Ioanna Karkatsouli. I have a bachelor's degree in electrical and computer engineering from the National Technical University of Athens and a master's degree in technology and policy from MIT. I have worked as a research assistant at MIT, doing economic modeling of climate change, then as an economic consultant at the Brattle Group, and until recently as a senior pricing statistician at Staples. Today I'm going to share some insights from my work at Staples. Some of my hobbies are coffee tasting, yoga, taking online classes of any kind, and reading books. So today I will be talking first about Staples briefly. Then I will share some analytics and data science applications for pricing that I find useful. Then why do we care about optimizing price and promotions? I will continue with a project example and particularly predicting the effectiveness of price promotions. And I will close with some key takeaways. Staples is an office retail company. The first store opened in Massachusetts in 1986, and today it has about 1,100 stores around the US. Staples North America is split in 3 different entities: US retail, Canada retail, and business to business. My team was part of US retail, and we were supporting its pricing function. There are plenty of applications in pricing that I think can benefit from analytics and data science. And I will share a few of them with you here. So in terms of pricing strategies, we can set up experiments to test different pricing strategies in stores or online, or we can determine key value items. In terms of price changes and markdowns, using, again, machine learning, data science, we can calculate price elasticities, or we can predict the effectiveness of future price promotions. We can optimize the clearance process, or we can try and match our products with competitive products and scrape the web for competitive prices. Today, we'll be focusing on one of these applications and particularly predicting the effectiveness of price promotions. Why do we care about optimizing price and promotions? Promotions account for up to a half of the revenue for brick and mortar retailers. However, around a third of these promotions turn out to be non-profitable. And most retailers do not really take full advantage of their data and of data science capabilities in order to optimize their price and promotions. However, it's more like critical now in the COVID era to run profitable promotions, since retailers are already facing a lot of challenges, especially the brick and mortar ones. Regarding our project now, let's start by giving some context on the business problem. Retailers, including Staples, they run weekly promotions usually, which are advertised in their circular that you can see here on the right. The question is, can we predict which products should be promoted and at what price on a future date so that the promotion is effective? And what do we mean by effective? We're looking at 3 main key performance indicators here, which are the unit, the sales, and the margin lift because of a specific promotion. Traditionally, merchants decide on which promotions to run for different products using some historical data and, of course, their experience. The approach is different by merchant, and it's usually not reproducible for different products. And it's hard to estimate additional cross-product effects. We'll talk about those later. Using data science, we can automate this whole process of figuring out which promotions are profitable, and we can also do this more accurately. So let's look at the data science tasks now. How can we break this problem down? First of all, we will need to predict how many units of the product will be sold or would be sold if there was no promotion on a future date. That is our baseline units. We will also need to predict how many units we expect will be sold with the promotion. If we look at 2 years of data of a specific product, let's say a notebook, the picture is something like that. So we will observe a couple of things. First of all, each year we see some specific seasonal patterns. We see some peaks on certain dates, and it turns out that at Staples, at least, in office products, there's usually a huge peak during the back-to-school period, and then some smaller peaks over the winter holidays, during the tax season, and this is repeated every year. And this is what we call seasonality of demand. We can also observe, since we have 2 years of data here, that there is an annual trend. So every year, there is the demand that turns to, unfortunately for brick and mortar retail, demand tends to decline. So this is a downward trend. Therefore, we need to create a model that will capture all of these effects. We ended up using a multivariate regression model trained for each product separately. The target variable were the weekly units sold by product, and the main features were the price of the product, the sequential week number. Since we have 2 years of data, this is 105 weeks. Therefore, we give each week a number from 1 to 105, and this will help us capture this annual trend. Then in order to capture the seasonality that we talked about, we added some Fourier terms, sine and cosine terms, and also we had some flags for the holidays and back to school. In addition, we added some features related to promotions, and these are the discount rate of the promotion and some other promotion attributes, such as on which page of the circular the promotion is located, on what part of the page, etc. So based on this, we have now our regression model. And here is the magic. If we run this regression only using the first set of features for a future date, then we can find the units baseline. So what would happen if we didn't have a promotion? Then if we run it with additionally these 2 last features that are the promo-related features, then we can find the units that would be sold with a specific promotion. So with this regression model, we have completed tasks 1 and task 2. Once we have these numbers, it is easy to calculate the direct unit lift over the promotion by subtracting the units that we expect to sell with the promotion minus the baseline units. And then once we have the unit lift, it is easy to calculate the sales lift and the margin lift. Then we will need to estimate some additional promotion side effects, I would say, which are the halo, cannibalization, and pull forward. And I'll talk about each one of those in detail. Halo is a positive side effect of a promotion, and it happens when promoting one item increases the sales of another non-promoted complementary item. For example, if we promote a laptop, then we will probably observe an increase in the sales of this laptop, but also we might observe an increase in the sales of webcams, for example, just because people buy those together. Since we're talking about products being bought together, in order to estimate halo, we would look at the basket or transaction level, and I will be using these two terms interchangeably. So one way to calculate halo, there are multiple ways, but what we did, one way to do this is to first average the non-promo item sales in transactions that have at least one promoted item. And this will be the average halo per transaction. Then find how many are the incremental transactions because of promotions. And then once we have A and B, if we multiply those, we will have the total incremental halo because of promotions. And then we just need to allocate this halo to the promoted items for the week, for example, proportionally to the regular prices and their total sales. Just because we expect that a more expensive item will attract more products with it, more non-promoted item sales. Second effect is cannibalization. Cannibalization is a negative side effect of a promotion, and it happens when promoting one item decreases the sales of another item which is in the same category. For example, if we promote a Dell laptop, we might observe a decrease in the sales of Lenovo laptops. How can we calculate cannibalization? We will need to look at the category level, since we're talking about the behavior of similar products in the same category. And again, many ways to do this, but here's one way that we can calculate it. We will first need, looking at historical data, we will need to add up the lift of individual promoted products within the category. And this will be the category lift that we would expect to see if the non-promoted products in the category were still being sold at their baseline. So this here would be the orange arrow. Then, assuming that we have a baseline for the category, which is the blue line, and then we also have the true units that were sold in the category, which is the gray line, we can calculate the true lift of the category, which is the gray arrow. If the lift that we expect to see, the orange one, is greater than the true lift of the category, then the difference of these two is the cannibalization, which is the red arrow here. Okay? Then the last effect is pull forward. This is a negative side effect of a promotion again, and it happens when customers stock up on a promoted item and then they don't come back to the store on the regular frequency after the promotion. So for the pull forward, we will need to look at the customer level data and find if the frequency of buying a promoted product changes following the promotion period. And if this is the case, then adjust the promotion lift for the lost revenue due to this change in frequency and due to the missed trips. And here I have an example to explain what I mean by missed trips and lost revenue. You can take a look at that. So once we have all these pieces, we can now calculate the final lift of the promotion as follows. The total margin lift would be the direct margin lift, which were the predicted promo minus the predicted baseline units, margin, I guess, in this case, minus the discount, plus halo, minus cannibalization, minus pull forward. So something like this graph. If the final result is positive, like this case, then we predict that this will be a profitable promotion, and we recommend that we run this promotion. So you can see this is a very useful tool for merchants and for the company as a whole, and it helps give some guidance as to which promotions we expect will be profitable. And merchants can use this tool. They can run, what-if scenarios, and they can decide on a set of promotions that we predict will have a positive margin. So key takeaways. Data science can inform pricing and promotion decision, and it is very important that such decisions are based on historical data analysis and modeling. And if we calculate the lift of promotion, the lift should be estimated with regard to a non-promo baseline and should include effects such as halo, cannibalization, and pull forward. So thank you very much for attending, and please let me know if you have any questions.